Okay, so we will switch gears a little bit and talk about some commonly used computer vision data sets, so that you have some rough ideas about, what are the standard benchmarks in this area. The most commonly used, perhaps, or the simplest of them all, is known as the MNIST dataset, which is a dataset for recognition of handwritten digits. Okay, so this is a very early data set published as early as 1998, and the success on this data set has led to applications in automatic recognition of digits in many different areas, such as ATM, right? So we know that in America, check is still very popular. I think in many part of Asia, we prefer mobile payments, but check is still very popular in America. And which is basically a piece of paper, and you have to write the numbers down, and you write down like who are you paying to, and so on. So in order to recognize automatically these checks, people have developed ATMs that can do that, right? So there are ATMs that can read checks within a few seconds, and there's some like AI technology in there, and that was built on the foundation of the MNIST dataset. So basically, the dataset contains a large number of well pre-processed digital handwritten digits in just black and white. Okay, so the digits, there are 10 digits from 0 to 9. The image size are pretty small, 28 by 28, and the numbers almost always appear very close to the center of the image. So the training set has 60,000 images with a test set of 10,000. The typical performance on this data set is well above 99%. Okay, so very close to 100%. I'm including this number uh, because I wanted to show you what is the reasonable number that you should report in your homework. All right, so sometimes I get um, pretty grandiose claims with rather unsatisfactory numbers to back the claims up, right? So, for example, people would say, I have proposed a improvement on top of the residual network, and then I tested on MNIST, and that I achieved 85% accuracy. And I would say that really does not demonstrate any improvement. Rather you might be doing something wrong, right? Because if you use extremely simple network or simply classic machine learning techniques such as logistic regression or SVM, you should get easily above, 98, 99% accuracy. So if you try something and you get way below that, that definitely indicate that something is wrong either with your program or with your network. Okay, so it's important to know where the reasonable bar for accuracy should be, right? So a slightly more difficult variation of the MNIST dataset is from it's called Street View House Numbers, or SVHN. So these are numbers that are taken off, I think, Google Street Views, and they have like the house numbers uh, in these images, and they're cropped and in a way that's somewhat similar to MNIST, so that you want to recognize the image that is in the center of the digit that is in the center of these images, um, because there could be something that, kind of happened before or after the center digit, but that's not what you're supposed to recognize. So the images come within like different sizes. So they're not like all the same size as in MNIST. The median height is still 28 pixels. And the training set contains like about 73,000 images. And the test set contains about 28,000. Typical performance on this data set is to the north of 95%. If you get something that is like 70%, you definitely have something wrong in your program. Another uh, commonly used data set that you could, use as a test if you're running small scale experiments is called fashion MNIST. So it is slightly more difficult than MNIST and SVHN. So the typical performance is about 89%. If you use some simple stuff, you should get to 89%. Um, Image sizes are 28 by 28, 60,000 training, 10,000 test. The images are basically silhouettes of fashion items like t-shirts and boots and things like that. So the classes are shown here. Uh, Next one is known as CIFAR 10. Uh, it is a full color realistic images or natural images, uh, and it contains 10 classes from airplane to ships and trucks. So image sizes are slightly bigger at 32 by 32. Training set and test set are of comparable sizes, 50,000 and 10,000 respectively. Typical performance is greater than 85%, which is not a very high bar. If you get to like 75% or 80%, you know that you need to improve things. ResNet 18 with very simple data augmentation techniques and training techniques should get to 83% with no problem, and pretty reliably it gets there, right? So if you get to 70%, then perhaps we need to revisit. CIFAR 100 is somewhat more difficult. It is still of comparable size to CIFAR 10, but it contains 100 classes, and each class contains only 500 examples, which makes this data set much more difficult. And typical performance, if you use simple networks, that should give you like about 65% or higher. The last one we will discuss is known as ImageNet 1000, also known as the LISVRC. I think it's International Large Scale Visual Recognition Competition, which was a competition that was held, um, I think maybe around 2009 to uh, 2015, 16 or something like that. So the ImageNet data set is a gigantic data set that tries to mimic the ontology of a dictionary, right? So it's modeled after a dictionary known as WordNet. Okay, WordNet is uh, an effort trying to organize all the English words into a hierarchy. Um, excuse me. Um, like animals would have subclasses like mammals and reptiles, and mammals would have subclasses like dogs and cats and so on. And the words could be connected with relations such as synonyms and things like that. So it's a very large database of words, and ImageNet wanted to give all the words images, right? But obviously there are concepts that cannot be easily visualized. But for those that can be easily visualized, they want to uh, collect a lot of images for these words or for the synset of these words, which is like a single meaning of the word. Because one word could have like multiple meanings. The word bank could mean the financial institution or the side of the river, and both could have their own separate images, right? So out of these um, big effort of collecting images for every synset of WordNet, they have extracted 1,000 classes, perhaps with distinct visual features, and use that as a test for the visual recognition competition. Okay, so this is the story of origin of the ImageNet 1000 dataset, and today it's still used as a strong benchmark for the for computer vision neural networks. The image sizes are like all over the place, but mostly are pretty big. And when we do recognition, we typically resize them to 2 to 4 by 2 to 4, or sometimes 256 by 256. The training set contains more than 1 million images, and there's a validation of 50,000 and a test of 100,000. And the best model in 2021 achieves above 90% accuracy if you look at top line accuracy, which means the most confident prediction, it is about 95% correct. The best model right now, I checked a few days ago, is above or around 95% accuracy. And it is estimated that ImageNet 1000 contains maybe about 4 to 5% of annotation errors, right? Because the data set is crowdsourced. The images are supplied by like people on the internet. So there are some errors in these data. And it is estimated to be around maybe 3, 4, or 5%. So we're already very, very close to the ceiling of the performance if you look at the best models people have built. Okay. But this is a difficult data set because of the computational power it requires to train for a few hundred epochs on 1.2 million images. So if you do use this data set in your homework, this would be, a great achievement, but you wouldn't be required to do so for the purpose of the homework or the course project. Okay. So with that, we conclude our discussion on convolutional networks, or the basic building blocks and architecture of convolutional neural networks. We will also talk about in later lectures more advanced architectures of convolutional neural networks, and as well as transformer networks. So that's it for today, and I'll see you next time.